Energy balance for biosystem. Module 7, Conservation of Energy. Segment 1, Basic Energy Concept. It's me Lily from School of Life Sciences and Technology, Institute Technology, Bandung. In this module, we will discuss about the basic energy concept, review of energy conservation statement, closed and isolated systems, and calculation of enthalpy in non-reactive process. In this segment, we will first discuss about the basic energy concept. After completing this chapter, students should be able to list and explain the type or forms of energy, explain how heat and work relate to energy, write the algebraic, differential, and integral form of the conservation of energy equation. And also, students should be able to apply the first law of thermodynamics, and student can describe the concept of enthalpy and heat capacity, calculate changes in enthalpy due to mixing and from temperature, pressure, and phase changes. And also can apply the conservation of total energy equation to open and non-reacting system, and calculate the heat of reaction using heats of formation and heats of combustion data. Apply the conservation of total energy equation to open and reacting systems, and apply the conservation of total energy equation to dynamic system. While fossil fuels are the most common energy source in nation, renewable energy sources such as wind, solar, hydropower, ocean, and geothermal are becoming more popular. An exciting new field in renewable energy sources is bioenergy, which exploit renewable biomass such as any plant-derived organic matter that can be replenished by cultivating fast-growing trees and grasses. And many biomass materials such as plant, agricultural byproducts, and organic component of municipal and industrial waste are now being used to produce biofuels and power. Although technologies for using biological energy resources are still being developed, the eventual benefits should be significant. And in addition to the technical hurdles involved in designing efficient systems, the economical, social, and environmental consequences of bioenergy must be taken into account. And the following issues associated with bioenergy systems can be seen in this slide, such as sources, evaluation, design, land use, water conservation, and safety. Multidisciplinary teams around the world tackle the problem of the best way to generate and harness bioenergy. And in this chapter, we'll open with the overview of basic energy concept and then discuss how system definition can be applied to solve system involving energy. In a basic energy concept, accounting for energy is important in a number of bioengineering applications, such as modeling energy gains and losses from the body, analyzing biochemical reaction, and designing and operating bioreactors. In here, we analyze the transfer of energy of various forms across the system boundary and its interconversion and also the accumulation of energy within the system. The total energy is conserved while mechanical, electrical, and thermal energy are not conserved. This is because energy is neither created nor destroyed in the universe, except for nuclear reaction, but merely change form. Energy possessed by mass. All mass possess energy. Energy is possessed by mass due to its motion, position in space, and the state at which it exists. And a body possesses potential energy as a result of its position in a potential field. And for example, the gravitational potential energy or EP of an object of mass m must be defined relative to a reference plane, and it can be calculated using the formula in this slide, where g is the gravitational acceleration constant and h is the height relative to a reference plane, and 1 and 2 denote the two different positions in space. And in other case, for the change in electromagnetic potential energy or EE can be calculated using the formula in this slide, where Q is the net charge, V is the electric potential energy per unit charge, and 1 and 2 denote two different positions in space. The difference in potential energy per unit charge is commonly called voltage. And also, we can calculate the change in the rate of the gravitational potential energy and also for the change in electromagnetic potential energy. And the symbol can be symbolized by using the dot. Beside of energy potential, a body or mass possesses kinetic energy as a result of its translational or rotational motion. In other words, kinetic energy is the energy of motion in terms of velocity and can be seen as the energy an object possesses while in motion. And the kinetic energy or EK of a system is calculated as Ek is equal to a half of mv square, where m is the mass of body and v is the velocity. And to distinguish between the potential and kinetic energy, an example can be employed. We can see this figure. A square object on top of slide has a certain amount of potential energy depending on its height relative to the ground. When the object begins to slide down, it is experiencing kinetic and specifically translational energy. The last form of energy present in a system is internal energy. Mass possesses internal energy by virtue of atomic and molecular interaction. And all energy possessed by mass that is neither kinetic or nor potential energy is internal energy. And the internal energy of a system is a function of temperature, pressure, chemical composition, phase, such as vapor, liquid, solid, or crystal, and other characteristics. While internal energy cannot be known in absolute terms, the change in internal energy can often be quantified. And for the rate of internal energy, or U dot, is the rate at which internal energy enters or leaves the system with a fluid or other material that crosses the system boundary. And a system's total energy is defined as the sum of potential, kinetic, and internal energies, and the formula can be seen in this slide. We can convert extensive variables to a specific variable which are defined by a circumflex accent or head by dividing by another extensive variable such as mass or moles. And the term specific refers strictly to the quantity of a variable per unit mass or moles. Specific energy is energy per unit mass or per unit mole. Specific energy rate is the rate of energy per unit mass or per unit mole. And the total energy is written in terms of specific variable. For example, in this slide is per unit mass. It can be written as mass multiplied by the total energy of potential, total energy kinetic, and the internal energy, where m is mass and E hat T, E hat P, and E hat K, and U hat are specific energy. In energy and transition, we talk about that heat and work are energy in transit across the boundary between the system and its surrounding. Heat and work can only be understood as the movement of energy through direct and non-direct contacts, or not bulk material transfer. And heat, or Q, is energy that flows due to a difference in temperature. And the direction of heat flow is always from a region of higher temperature to one of a lower temperature. Sometimes the heat or rate of heat is specified, and one of the simpler methods of estimation relates the rate of heat, or Q, to the effective surface area over which the transfer occurs, A, and the temperature gradient can be calculated as the Q is equal to the H multiply A and multiply temperature of surrounding minus temperature of system, where H is the heat transfer coefficient per unit area, and T sir is the temperature of the surroundings, and T6 is the temperature of the system. And heat can be defined as a positive value when it is transferred to the system from the surrounding. And in other words, heat is a positive value when it is added to system. Beside of heat, work or W is energy that flows across a system boundary as a result of a driving force other than temperature. One type of non-flow work often encountered in this study of thermodynamics is associated with the contraction or expansion of a system volume against an external force. And the differential work on the system, or dW, is written as in the slide, where dx is the differential distance or the displacement, and the force Fx and the displacement or dx are defined to be in the same direction. We have to remember that work is typically classified into two types, the non-flow work and flow work. For the non-flow work, we already discussed in the previous slide. And for the flow work, we can say that the flow work is the energy that required to push matter into or out of the system. A fluid flowing into or out of a system has work being done to it to move the fluid across the system boundary. And the integral form that relates to work, the force, and the differential distance dx can be written as the equation below. And also, we can calculate the terms of the rate, and also for the differential form we can write as the following equation, where t0 is the initial time and tf is the final time and v is the velocity in the x direction, and the rate of work is also known as a power. Consider a system with fluid flow entering the system with velocity v, because force is pressure multiplied by area. The rate of work, or W dot flowing into the system, can be written as the equation below, where P is the pressure where the fluid crosses the system boundary, and A is the cross-sectional area of conduit carrying the fluid. And also for the rate of flow work on the system, or W dot flow is the difference between the rate of work done by the fluid at the system inlet and the rate of work done by the fluid at the system outlet. And the equation can be seen in this slide, where I and J are different inlet and outlet stream respectively. The last part of this segment is enthalpy. Enthalpy or H is a thermodynamic function that is defined as H is equal to U plus PV. And also for the rate of enthalpy or H dot is the rate at which enthalpy moves with fluid or other material. And it can be calculated as the H dot is equal to U dot plus PV dot, where U is internal energy, P is pressure, and V is volume. We can also calculate the specific enthalpy, and we can see the equation in this slide. For the next segment, we will discuss about the review of energy conservation. Until then, I'm Lily from Institute Technology Bandung.